So look at this problem, amplitude modulation and savings on bandwidth. So as a quick review, we have a signal f of t, and we look at its Fourier transform. That will give you an idea about bandwidth and so on. So Fourier transform is defined as ft as from time to bandwidth. So through this transformation in general. So it's a function of frequency. And if you plot it, and if a signal happens to be this, we call this to be its bandwidth. So this is the two-sided bandwidth. B0 is the one-sided bandwidth. So in this case, it's a band-limited signal. Suppose ft is real, then the Fourier transform has got, so which is the case with voice, video, etc. We usually transmit real signals unless you purposely create a complex signal by a quadrature component also. So if you can see that if you substitute into this relation, we get some interesting relations. F omega is ft e raised to minus j omega t, which I'm going to write it as cos omega t minus j sin omega t dt. So this, of course, has two terms now, ft cos omega t minus j integral ft sin omega t. So these are the real and imaginary parts. So let me use the usual symbol rx omega minus jx of omega. So r and x are real functions, but this is called the real part of x f of omega, and this is called the imaginary part. Notice that the imaginary part is also real because the ft is real, sin omega t is real, this is real. But you can see when you change omega to minus omega, cos, this is the only place where omega comes. So cos minus omega t is the same. So r of omega has this property. This is an even function. And similarly here, if in x of omega, if you change omega to minus omega, sin minus omega t is minus sin omega t. So this turns out to be x minus of x of omega, or this is an odd function. So the whole point is if ft is real, you only need this information here. You can, if this is omega, you can duplicate the information here. So f of minus omega would be r of minus omega plus x of minus omega, which is, we can find it from f of omega. So f of minus omega is r of minus omega plus or minus the minus jx of minus omega, because f of omega is r of omega minus jx omega, the way we defined here, because of the minus here. So this comes, because this is even, this is r omega, because this is odd, this becomes plus x of omega. But you can see this is the same as f star of omega, because f omega is here, f star of omega is here. So we get the relation, any information at the minus frequency is actually obtainable from here. So what so it's pretty clear that there is, all the information is here. The information here is just to duplicate it. All right, so with that in mind, but it's a, you cannot make this 0 because this, if the original signal is real, then the this quantity x is on the negative side. All right, now what is modulation? Modulation is you transfer this information to a different frequency for transmission purposes, because this is called, usually called baseband, whatever hangs around the zero frequency. And transmitting, if you even audio or anything at a low frequency, the propagation losses are very high. So you do want to make it as if this is being at a higher frequency where the transmission losses are less and less. So that method is modulation. To see that, let's see, what the transform of ft e raised to minus j omega t is. What's the transform? So if you do the Fourier transform of ft e raised to minus j omega naught t, in other words, if you, this is like a phase shift, or multiplying by a factor of omega, slope of omega naught, right? So multiplied by e raised to minus j omega t dt. So that's going to be ft e to the power minus j omega plus omega naught t dt. So that's the Fourier transform evaluated at omega plus omega 0. So this is the Fourier transform evaluated at omega plus omega 0. Similarly, we get ft e raised to plus j omega naught t is f of omega minus omega 0. So if you add these two, you can see that you can generate the cosine. So if I add it and divide by 2, you get cosine omega naught t is actually f of omega minus omega 0 plus f of omega plus omega 0 divided by 2. So pictorially, if this is f omega, you have f of t, some information, and this is f of omega. But the transform of ft cos omega naught t pictorially looks like this. It gets shifted to these places. So omega naught and minus omega naught. So this very process is called double sideband modulation or amplitude sideband modulation. You just transmit a carrier also. So if I call this to be g of t, this is g of omega, or let me call it f1 of t. So this is f1 of omega. And as I said, in amplitude modulation, the transmitted signal is something like some amplitude 1 plus lambda ft cos omega naught t. So lambda is a constant. So this purpose of the lambda is to make this whole thing non-negative, so that it's very easy for decoding or detection, demodulation purposes. But in terms of a transform, all you are doing is, if you call f, so the transform of FAM has two components. One impulse at because of the cos omega naught t, and then on top of that this one. So you could call this this is called the double sideband modulation, DSB. This is AM modulation. So what's the problem in both of them? Notice that previously I said if you look at the information here and the information here, they are the same because you can obtain the one from the other, as I said before here, right? This information here, if I call this some frequency omega, then the corresponding information at minus omega is obtained by this relation. So the value here is simply the complex conjugate of this. So in essence, you can see when you duplicate, you are occupying this much bandwidth, but only the half of it is, it's actually duplication of information. So we conceivably we can save some bandwidth here by getting rid of either the lower band, which is in red here, or the upper band. So when you shift it, this will become blue, and this will become red. So either you can keep the blue region, which is here it is the beyond omega naught, so we call this the upper sideband, or the lower region, lower sideband. But this because of this but again, if you want whatever you do, and ultimately if you want to keep a real signal, then you have to worry about this relation, which means that if you have something at a positive frequency, its negative frequency value is inevitable. You cannot make this zero. So you can only have two schemes. Whether you can either you can keep the upper sideband, or you can keep the lower sideband. But you don't have to keep both. So both in amplitude modulation and DSP, we keep both, but it is both sidebands, the upper sideband and the lower sideband. But that's a penalty. So that's a loss in terms of bandwidth, especially if bandwidth is premium, then you are wasting bandwidth here. But the advantage is extremely simple to modulate. Either you just multiply by a carrier and transmit, or add a carrier and transmit. As I said, if ft is like this, if this is ft, and suppose you choose, suppose you find the maximum value of ft and choose lambda to be less than or equal to 1 over the maximum value of ft. In other words, you choose m to be the maximum value and lambda make it. So then you can see this number will be in always between -1 to +1. So 1 plus this will be non-negative. That's the whole point of making this multiplying by a constant here. Consequently, if you modulate here directly, look at this. If you if you modulate this directly, it will look like this. So notice from here, when you come to these points, there will be ambiguities. We wouldn't know whether the signal goes this way or this way. So to avoid that, suppose we do this 1 plus lambda ft, which would look like this. That same signal will now look like this, all on side. So now if you modulate, of course, it's going to look like this. So this is AM, this is double sideband modulation. So that's what we have discussed so far. So the question is, how do we save bandwidth? And this is where, so something need to be done. So this is where the Hilbert transform comes in. So Hilbert transform is a frequency operations. Best to explain there. Initially, it may not make sense. Suppose we have a transfer function which is like this. So a sine function is like simply what it says. SGN is for the sine function. So it picks up the sine, SIGN, but usually it is written as SGN. So it is +1 when omega is positive. So sine omega is +1, omega is non-negative, and -1 when omega is less than 0. Here I am multiplying by -j. So you see, notice that -j is like shift by pi by 2. So you can also say in the frequency domain, this. So in other words, if you want, you can write this as e raised to -j pi by 2 sine of omega. So this is a phase shift by plus pi by 2, pi by 2 or minus pi by 2, depending on the frequency. So you could also interpret it that way. But this is sort of a crazy coming out of nowhere. The question is, what is its usage? What is the corresponding waveform in time domain, etc.? And moreover, how is this going to help in saving the bandwidth? This will help. So that's what I'm going to show. First, let me find out the impulse response in the time domain. So that, not that we need it, but at least you know how to get the Hilbert. So to get a Hilbert transform of a signal, this is what you do. If you multiply a signal with this function, we get a new we call it the Hilbert transform of ft. So the corresponding time function is f hat of t. So frequency domain multiplication, as some of you may know, that's the in time domain that translates to convolution in time domain. So in any case, this is -j sine omega multiplied by f omega. So let me find out. So we can also write f hat of t is ft convolved with h of t. So if you want to implement, you can implement it this way, provided you know what h of t is. Now remember, ft is a real signal. So you will see, but the way these things are set up, this will also turn out to be real. So let's see it right away. So I need a property called the duality property to do this easily in the Fourier transform. So that goes like this: if f omega is the Fourier transform of ft, then we can get ft this is the Fourier transform relation. And as you know, the inverse Fourier transform relation is 1 over 2 pi. The limits are wherever they are. I'm going to write it in general as minus infinity to plus infinity. So then the ft is f omega e raised to plus j omega t d omega. So you have two relations, Fourier transform and inverse. So generally the first relation is shown like this. And these two relations are shown like this. This means ft in time, this is in the time domain, and f omega in the frequency domain follow a Fourier transform pair. Now look at what I'm going to do. I'm going to take the second expression and rewrite it this way. So I'm going to multiply it by so it gives 2 pi ft is minus infinity to plus infinity f omega e raised to my plus j omega t d omega. So I'm going to replace omega by, omega is a running variable, so I'm going to replace it by x, and t I'm going to replace it by y in the next line. So this now reads 2 pi fy equals fx e raised to j xy dx. Now I'm going to, this is an equation, so I'm going to replace this by minus omega. So y becomes minus omega. I'm going to put this x to t, another running variable. So this now reads 2 pi f omega, 2 pi f of minus omega. It's minus infinity plus, it's just a small tricks, ft e raised to minus j omega t dt. Look at this expression and compare it with 1. So you can see that if capital F omega is the Fourier transform of small ft, from here it would mean that this quantity 2 pi f of minus omega is the Fourier transform of this shape. So let me capture this relation. This I'm going to call it 3, and from whatever is coming out of these two relations. So what we just found that if ft has a transform f omega, and if I bring in this shape into the frequency domain, into the time domain, then its a transform is given by related to this in this fashion. So I'm going to call this, this is the duality rule. So very useful. So this, for example, if you know that the transform of a pulse is sinc, right? So let's say minus t by 2 to t by 2. So this will be sinc omega t by 2. Just do it directly. And I think this is, let's say, some height a. So this may be, I think it is ta. That's the transform. So what it says is, if you want the transform of sinc, let me put the t equal to 2. Then you get the transform of sinc t equal to 2 is just this in the frequency domain. So I put, and I put a equal to t equal to 2 and a equal to half. So a equal to half and multiplied by 2 pi. So it's simply pi, I think, right? So you get this. So if a single function which is in time domain has a transform which is a rectangular function, etc. and etc. So here, so for example, delta t has a transform of what is the transform of delta t? So that's integral delta t raised to minus j omega t dt, but that's just one. So that's a constant function. So that would mean that constant function has a transform of 2 pi delta of minus omega, which is the same as 2 pi delta of omega. So let's go back to our problem. Our problem is to find the Hilbert, find the impulse response corresponding to this Hilbert transform operation. So that will be, so remember, h of omega is minus j sine omega. So sine omega is like this. So if I take the derivative of h omega, look at here, you will get an impulse, 2 times the impulse. So this is minus 2j delta of omega. So the whole idea is to figure out the h of t. I'm going to do it with some of these properties. So I have delta omega here. Oh, one more property is, remember, if h omega is as the transform, h omega is actually h of t raised to minus j omega t dt. So if you take the derivative on both the sides with respect to omega, you get this this operation. So we also see that h prime omega is the transform of minus jt h of t. So here, let me go here. So this we can write it is minus jt h of t. So minus jt, so I'll rewrite that expression here. Minus jt h of t has a transform which is here minus 2j delta omega. But we know the transform of delta omega because look at here. We had this expression. Right? One has a transform of 2 pi delta omega. So we also know that delta omega has an inverse transform. So if you call this to be some g of omega, then the corresponding time function is g of t. So delta omega has an inverse transform of g of t. So if you look at the inverse transform of this, inverse transform is going to be minus 2j divided by 1 over 2 pi from that previous graph. Delta omega has an inverse transform of 1 over 2 pi. So an impulse function here is a pulse of is a DC essentially. And similarly, the inverse transform of this, which is written here, I'll write it here, jt h of t. So I can equate to these two quantities. Minus j cancels, 2 cancels. So you get a h of t equal to 1 over pi t. So from here you get h of t equal a simple result. This is the Hilbert transform impulse function if you are interested. So what's the whole point? The whole point is if I define this fancy transform called minus j sine omega, whatever is this transformation, we know that its impulse response is simply 1 over pi t. So I'm going to transfer h of t to this. So ft goes through h omega, which is the same as I'm going to call the output to be f hat of t. So in the time domain, this is simply ft convolved with 1 over pi t. So if you want, you can write. I'm not saying this is the best way to implement, but we could write it like this. So everything is real. If ft is real, h of tau is real. And now you can see one of the reasons why. So this is a nonlinear function. Something is getting flipped. So it's we still haven't. I qualitatively explained to you what this is. So phase shift by pi by 2 for positive frequencies, and by minus pi by 2 for negative frequencies. All right, so let me consider, so that being the quick introduction of a Hilbert transform, let me show you the usefulness of FT, I mean a Hilbert transform. So I'm going to do the Hilbert transform. This is this operation. So the output here is f hat of t. So I'm going to do this modulate by cos omega naught t and modulate this with sine omega naught t. Then I can add or subtract. So I have two things. And I'm going to call this, let's say, x of t with a plus sign. And with the minus sign, you can call it y of t if you want. So plus sign means both are added or one is subtracted from the other. And let's see what that. So remember, everything is real in this block diagram because you have a real signal coming in. I took the pains to show that the impulse response is real. So this is still real. Sine, cos, everything is real. So you can actually indeed do this. Let's see what is the bandwidth of x of t. So x of t is ft cos omega naught t plus f hat of t sine omega naught t. And if you take this form, we already know it's transform. It's sitting around. We did it a few pages back. Ft cos omega naught t, which was the transform of all right. So Ft cos omega naught t shifts the transform to f omega to centered around omega naught and minus omega naught. So also these properties will be useful. So we had ft e raised to plus j omega t to be f omega minus omega 0, and ft. So I'll copy that here. So we had ft cos omega naught t. If you we already derived that this is has a transform of 1 over half f of omega minus omega 0 plus f of omega plus omega 0. So question is, what is ft sine omega naught t transform? I think, so you can see we have both the terms. Sine omega naught t is obtained by this minus this. So this is common. So if you subtract this minus this and divide by 2j, we'll get, remember, Fourier transform is a linear operation. So it's 1 over 2 pi this minus this, 2j. So that's 1 over 2j f of omega minus omega 0 minus f of omega plus omega 0. But if you notice here, we want f hat of sine omega naught t. So let me do f hat of sine omega naught t is whatever is the transform of this gets shifted. So let me substitute, but f hat of omega is, we know from earlier, minus j sine omega f omega. So let me substitute that into here. So we see that f hat of t sine omega naught t has a transform of, so this, you notice that the j will cancel because of the minus sign. This will get flipped, so you get 1 over 2 sine omega plus omega 0 f omega plus omega 0 minus sine omega minus omega 0 f of omega minus omega 0. So we'll get this much. And I'm going to write the other one just below this, cos omega naught t. I'm just going to copy from here. Because it is plus here, I'm going to write it that way, f of omega plus omega 0 plus f of omega minus omega 0. Notice we brought everything in terms of f and the sine functions. There is minus here, there is plus here. So all we have to do is just add these two terms. That means we add it on the right side, which I'm going to do now. So we have f hat of, I'm sorry, ft cos omega naught t plus f hat of t sine omega naught t as a transform of, if you, from the previous page, 1 plus sine omega plus omega 0 multiplied by f of omega plus omega 0, and then plus 1 minus sine omega minus omega 0 multiplied by f of omega minus omega 0. So let me just draw it graphically. We'll do the two terms and add it up. So let me take this term. This is second term. This is first term. Let's say. So omega plus omega 0. That's omega equal to minus omega 0. So that graph is here. So this is f of omega minus plus omega 0. This is 0, this is omega. And so sine function at omega, it flips the sign here. But then when you add 1, remember sine function is, so sine function is like this, plus 1, minus 1. If you add 1 to it like this, so notice that this will cancel, and you will get just 2 times the unit step function. This is, so this is the function 1 plus sine omega. So either that is shifted or to the up or down, but so that's 1 plus, and let's also do 1 minus. So we have, so this goes together. Here you have some 1 minus sine omega. So 1 minus would mean like this, and then you add 1 to it. So the other side cancels also. You get basically this. So this is 1 minus sine omega. So notice that this function, 1 plus sine omega, comes and sits here. So, and then when you, and in the other case, we can do it here. In the other case, you have f of omega minus omega 0. So these two, when it multiplies, you notice that here you had, previously we had, so when you multiply this, notice that the red portion goes away, and you only pick up this portion. So this is minus omega naught, and this is this we pick up this information. Let's see on the other side. So this is the first term, and the second term is f of omega minus omega 0. So omega 0 is here, you get, so this is f of omega minus omega 0. And so this function is 1 plus sine omega plus omega 0. These two are multiplied. And here we are shifting 1 minus sine omega. So it will be this function. So this function is 1 minus sine omega minus omega naught. When you multiply these two, you can see you are picking up the lower sideband. So this region. So this is blue, and this is red. So this is the lower sideband is picked up, and if you so this is x of omega. So notice that here it's only b naught instead of 2b naught. So half the bandwidth has been saved by bringing in lower sideband compared to the double sideband modulation. In the previous case, if you didn't do the Hilbert transform, you'd be transmitting both the sidebands in DSB. But as I said, this transmission becomes a little more complicated because now you have to worry about how to implement Hilbert transform, and it has got sharp edges. So those filters are going to be practically difficult. So if you do it with the negative sign, you'll pick up the other band. So I'm going to leave it to you. So the two sideband modulations are ft cos omega naught t plus f hat of t sine omega naught t. So I'm going to call this x of t, and the other one is the same thing with a negative sign in the middle, cos omega naught t minus f hat of t sine omega. So this is the lower, this will result in the lower sideband, this will result in the upper sideband modulation. So one is, so x of omega is like this with the lower sideband, and the other one is with the upper sideband. So this point is omega naught plus b naught. So you've saved half bandwidth, so you can pack in another signal there if you want. So this is y of omega, x of omega. So this is the implementation is, as I said, using the Hilbert transform. So f hat of t. This is not the best way to implement, but at least you can see the why it will stay real is 1 over pi t, and in frequency domain is phase shift by plus 90 degrees and minus 90 degrees. Now to approximate the Hilbert transform, you can because you can design filters with a minor leak, which takes up a little more bandwidth than B naught, but the advantage will be to be implementable. There are many ways you can design that filter. So that modulation scheme is called vestigial sideband modulation, which I will speak at some other time. So this is all I wanted to say at this point. Thank you.